Good morning. Good morning, everyone. Today, Stami Carbon will share with you some interesting topics. First of all, I want to thank the AFA organization and host OMIFCO for inviting us here, so we have the opportunity to share with you some interesting topics. Introducing myself, my name is Roel Trinis. I'm a mechanical engineer. Before I started with Stami Carbon, I worked for more than 15 years in oil and gas, more on the utility equipment. Since more than 2 years now, I'm working for Stami Carbon. I'm working at the after-sales department, so for support of all existing urea plants, so Stami Carbon and non-Stami Carbon customers. With this presentation, actually, I want to share some of the services and products we can supply to you as a support for optimizing your operations, but also to maintain your plant. Okay, little bit about Stami Carbon. Stami Carbon is a world leader in licensing and design of urea plants, with related services, including proprietary equipment. So we have our own proprietary material, which is called Safarex. The Safarex, we will have a very interesting presentation later on by one of my colleagues. And we are a pioneering company with a vision to enable the world to feed itself and improve the quality of life. Okay, Stami Carbon is located in the Netherlands, and the Netherlands is actually known by its tulips. Maybe you have visited Netherlands before. The windmills. We have the wooden shoes. Actually, we are not walking on that much anymore. It's not so comfortable. And of course, the cheese. The red dot, I don't know if this is working. Yes, the red dot, this is actually where the head office of Stami Carbon is located. So it's in the south of the Netherlands. It's quite near to Düsseldorf, Essen and Cologne. Stami Carbon used to be the know-how and engineering company of DSM, which means actually the Dutch state mines. And it was already established in 1974. So we have more than 70 years of experience and built up know-how in the urea process. We have a large number of references, so we have more than 250 urea plants licensed, and we, in the meantime, realized more than 100 revamps in urea plants. And since 2009, we are part of the Mare Tecnimont group, which is a large EPC company in Italy, Milan. Okay, now coming to the full life cycle philosophy. Stami Carbon is known from its licensing products and services, so creating new grassroots plants. But besides that, we have set up the after sales to optimize and keep your existing plant running in the best way. And we have a department which is called Evolve, which is there to even upgrade your existing plants, so to increase capacity or to have any kind of revamps for reducing energy and to increase the capacity. Also for that, we will have a very nice presentation which goes more in depth by one of my colleagues. Okay, just to come back on the operational and maintenance part. So we have actually divided our product and services in 5 main key products. So one is to maintain your plant. We have products to ensure good quality. We have compliance with the SHE, so with safety, health and environment. Optimize the process and training. So also the last part is a very important part what we supply. So we see also especially also in this field, a lot of new engineers entering the company, experienced people leaving companies, so knowledge is somewhere a little bit going back. So for that we are there to train also the staff and your employees. Okay, to maintain your plant. So what we do as Starmy Carbon, we have our, as mentioned, the equipment supply with the Safarex material. Here we have more than 20 years of operational experience with this material, and we have more than 140 high pressure equipments in operation with this material. So as you can see here, we have a lot of other services as well. I will not go into full detail for all, but especially also relining like your reactors. We have done so many projects with this, so we can support you with the full procedure, new relining material, so we can take this as a full, let's say, turnkey project. Very interesting also is we have a Starmy Carbon design for granulation, where we developed our own nozzle. This to improve actually the cycling or the cleaning cycle of the granulation. Okay, I will go also to inspection, because there is actually where we have a lot of experience gained during the 70 years. We mainly focus on the high pressure synthesis section of the urea, because this is the critical part where you have a lot of corrosion issues. And there we do our inspection. We have, together with other partners, we have developed our techniques to do the measurements, remaining thickness measurements of tubes. On piping, we have our lifetime assessment. Also today, my colleague will go more in depth on this topic. What we see a lot is that people focus on the high pressure equipment, the high pressure vessels, but they neglect a little bit the high pressure piping. But the high pressure piping is as important as the high pressure vessels actually, because they are also exposed to this highly corrosive urea carbamate solution. So for that we will have some interesting presentation later on as well. Okay, we can help you in inspection of ammonia tanks and also exterior inspections. For monitoring, we have some brochures over there. You may be interested, you can have a look. We have our leak detection monitoring system. This is more to provide you an early detection in case of a possible leak. This is based on an ammonia sensor, analyzer actually. So after installing this, you are able actually to detect in an early stage any possible leakage between the liner and your pressure bearing part of the high pressure equipment. For Starmy Carbon technology, this is now for us a mandatory equipment to be installed in the plant, since it's also a safety equipment. We have unfortunately seen a few accidents in the past. Recently also we had in Egypt a another incident with a scrubber where there was a leak. Finally, fortunately, we could repair this with the technology and the know-how of Stamik Carbon. But the leak detection system would have been of help in this case. People who know Stamik Carbon, they for sure know this gentleman. This is our senior inspector. It's Mr. Roest, Joost Roest. He's already very long with Stamik Carbon, so people who are in Stamik Carbon, they've seen him many times. Okay, some products to improve the quality. Actually, this is maybe less interesting for the Middle East because you are mainly making granules. But for prilling, we have a coating which avoids caking, so it's an anti-caking agent. And we have some very good experience with this. Here you see actually the product. It's actually an own developed nozzle which is spraying the product on the belt. And this is really taking care that the anti-caking is almost gone, even though you store it for a long time. Here also, this is some design with a prilling bucket, and we have some prill impact strengthener, but I will not go into detail since here in Middle East we do more with granules. Okay, some products related to health and safety. Thermal treatment, this is actually an equipment which we apply if you use a lot of nitrogen for the flare. So a lot of nitrogen which is needed for blanketing, but also for if you are using a lot of gas for the flare. This is actually quite an interesting package, and it's actually there to avoid that you have a high consumption of nitrogen. If you have any more interest in this, I can share with you some more information by email or later on. Wastewater treatment, of course, there we can do some studies to improve the load on the wastewater treatment. And we have some monitoring on the emissions. So we can measure emissions, and we even have the scrubbing technology on granulation to reduce the dust and ammonia emission. At the moment, we are developing a scrubbing technology which is using no acid washing. So this is almost ready. Once we have done this full study, then we will also make it available in the market. Good. Assisting during your process operation and control. Of course, we have the full assistance during troubleshooting. We can do process plant assessments to check where we can improve your process. And again, here the monitoring systems. So besides the leak detection system, we have level measurements where we use the radar technology, which is actually a very safe technology to measure your level in the stripper or in the reactor. And this is actually based on a signal which is sending a signal through a guide pipe, measuring the level in the pipe, sending a signal to this level and calculating the distance and giving you the level in the equipment. And this is actually eliminating the requirement of a radioactive source. Yeah, so it's a much safer equipment. Also here we have really a lot of experience already, a lot of references, and it's helping you a lot with eliminating the radioactive source. Okay, some insights. Maybe this is just to hook up with some previous interesting presentations. Also the presentation of Mr. Tarek yesterday. Here, actually, we are offering the same, more or less the same. We have the knowledge, of course, with all the process thermodynamics and the kinetics. What we do, we translate this in an as-is model. So we make together with you an as-is situation. After that, we can actually get feedback from the plant and compare it with this as-is situation model. As explained also in previous presentations, what we can do here, we can see if there is somewhere a deviation. And in case there is a deviations, this might be an indication of something is wrong in the plant. So it gives you really a nice indication of what is happening in your plant, which you may not be able to see without this information. Finally, we have a third step, which is automation disk control. So we can look within the boundaries of the operation of the plant. We can find the best optimum or maximum optimum spot to operate at. So this is actually what we do also with this advanced insight and then purely on the urea operation. And as you have heard before, the urea operation and process is quite complicated, but we managed with our know-how to control this. We have done actually a few projects, and depending on how good the client or you are able to operate the plant, we can gain a significant benefit. We have done projects where we achieved more than 4% extra output, and we reduced by 8% energy consumption. Okay, training. Here actually you see some of our trainings. We can do this in our house. We have a specific facility to give the training, but we also do this, of course, at site with our clients. So we can train on mechanical. We have a very nice simulator, again using our thermodynamics and kinetics. Together with a partner, we have set up this simulation training and simulation software, which is actually very, very close to the real operation of a urea plant. We have received very positive feedback that it's so near to the real operation of a urea plant. Okay, of course, process technology. This is our core business. We have our proprietary equipment, Safrix, where we provide the welding training, and we have specific safety, health, and environment trainings, also on process and also on emission. So we have a full product for this trainings as well. Okay. Now, actually, I want to introduce the trainings for today. You may have seen it in the agenda. So, first, after this, we will share with you experience and new developments of the Safrix material, which is given by my colleague, Mr. Kirk Offey. He is a material and corrosion specialist. After that, we will share with you improving energy efficiency in urea plants, done by Mr. Rahul Patil. He is our process specialist. Again, by Rahul, we will do a case study. Very interesting. This was a case where we had active corrosion after isolating the reactor. And as last one, we will do a lifetime assessment. So what I mentioned before, this would be on high pressure piping. So we do specific measuring techniques. We set up a specific program. But again, here, Mr. Kirk, he will explain you in detail what we do over there. Okay, that was it. Good job.
Oh, good morning again. This presentation is about experiences and new developments in Saphorex. Since we are all from the fertilizer world, I'm sure that either you are operating some equipment and piping with Saphorex or you know about this material. And this means that you probably have quite a few questions for us on this. So I'll just say that just feel free to interrupt with questions as I go through the presentation. As operators of urea plants, I think you are all aware that one of the main issues with operating a urea plant is the issue with corrosion. And this is because although you start with ammonia and CO2 as your feed material, you go through an intermediate phase of ammonium carbonate, which at high temperatures is quite corrosive. So if we go back in the history, actually the commercial production of urea became possible with two things. First, the development of the 316L urea grade material, plus passivation of this material with the addition of oxygen. So in the 70s, Stami Carbon, for the first time, teamed up together with our materials development partner, which is Sandvik, a specialty steel manufacturer in Sweden, to come up with a material that will be better than the 316L urea grade in terms of corrosion. This material is the 2522-2 or 2RE69 as is known. And for those of you who operate Stami Carbon plants, this is what we designate as BCO5. This material did indeed perform better than the 316L urea grade, which actually has higher chromium than the standard 316L grades. But as time went on, because Stami Carbon is a company that believes in innovation and in excellence, we decided that, well, there can be an improvement on the austenitic stainless steel, so we should look into this a bit furthermore. And at that time, they teamed up together again with Sandvik to come up with a material, and there were a few goals. So first of all, this material should be better in corrosion resistance than the austenitic materials. Secondly, the weldability should also be good. They also looked at mechanical properties. And then the last point was they would prefer it if the material can perform in less oxygen or actually zero oxygen. After a lot of effort, in 1996, Saphorex was introduced to the world. Since then, Stami Carbon actually specifies Saphorex as the material of construction for the high-pressure equipment in our plants and also for the piping. This schematic over here shows our pool condenser concept, where you have the pool condenser, the HP stripper, and the reactor in Saphorex. If it's a conventional plant, then you have the HPCC and the high-pressure scrubber also being made of Saphorex. Rule just mentioned radar level measurement systems in his presentations. Yep. These are also, because they are found in the reactor and the stripper, they are also made in Saphorex currently. To better understand, let's say, the performance of Saphorex, I think it's a nice idea to look at the corrosion issues that you face in your plants, especially with relation to the austenitic stainless steel materials. Here I'm using the Stami Carbon codes, but whenever you see BCO1, that's the 316L urea grade, and then when you see BCO5, that's the 2522-2, so that's the 2RE69. Condensation corrosion. Now, this is a severe issue for vessels which have a gas phase or pipelines as well. So normally when you have either poor insulation or if a vessel or pipeline is traced, but then the tracing is below the dew point of the process gas, Or if you have external attachments like trunnions or lifting lugs, you can have the issue of condensation corrosion in a vessel or a pipeline. This is quite dangerous because it is a localized corrosion phenomena. When you are outside the vessel, you cannot see that it is happening. And point two, the corrosion rate at the location where condensation corrosion is occurring is several times higher than the corrosion that you get in the liquid phase. There's also the phenomena of strain-induced intergranular corrosion. And in the urea synthesis section, this phenomena is also associated with gas phases. So where you have condensation corrosion occurring, and you have typically in the heat-affected zone of welds, where you have residual strain, underneath the oxide layer that forms in the condensation corrosion area, you can have cracks beginning to propagate. Normally, we see this in the hemihead of urea reactors, but more and more we see this also in pipelines made from the austenitic stainless steel materials, and actually also in the plate material used for lining vessels, which are quite old. Crevice corrosion is another issue that has to be dealt with. And actually, in the stomach carbon design, when the material of construction was the austenitic stainless steel materials, crevices were a big no-no in our designs because we do not allow them. Since when you have a crevice, then you create oxygen-free conditions which allow for a very fast corrosion rate. Another issue is fouling. So this picture over here is of a liquid divider. And you can see that the liquid divider holes have been fouled with a mixture of oil and oxide deposit. When you get a situation like this, it means that you are not getting enough liquid into your stripper tubes. So the stripper tubes run wet and dry. And this, when you are operating with the austenitic materials, can lead to the rupture of your tube. Active corrosion is also an issue, and this happens when you have stagnant conditions with ammonium carbonate, or if you are running under oxygen-free conditions. And the picture shows how detrimental that this can be. Cross-cut end attack. This not so nice picture here is of BCO1 tube, probably from a high-pressure carbonate condenser. This is an issue that we dealt with a lot when these vessels were constructed with this type of material. And another issue that is familiar with the austenitic stainless steel materials is chloride stress corrosion cracking. This also normally is associated with the HPCCs from the shell side. When we introduced Saphorex, we realized that just by changing our material of construction, we've eliminated all these corrosion issues. And when it comes to the cross-cut end attack, there are two issues. So when you have Saphorex tubes, yes, at the cross-cut phase, there is some slight attack, but it does not it is not a life-determining factor of your vessel. But also, we had certain equipment which were made in Saphorex, which have cross-cut phases, which had some issues, and we solved that issue by having another development in Saphorex, which I will talk about towards the end of this presentation. And over here, I show a slide which shows all the various forms of corrosion issues related with the austenitic materials and the vessels in which you typically find them. Now, to make it more clear, what I'm going to do is to show a few slides with specific corrosion issues related to the austenitic materials, and then show you how Saphorex performs under similar conditions. So this slide shows a liner material with a weld on it. The liner material is a 316L urea grade. You have a weld with a pore, when you have austenitic stainless steel materials, this is quite a dangerous situation, because what happens is that you create a crevice situation here. You have ammonium carbonate going into the pore. You have high temperature, but then inside this pore, the oxygen conditions are quite low, almost zero. What happens is that behind the weld, you start attacking the liner, and you end up in a situation like this. And the corrosion rate under such conditions is quite fast. So we have a similar condition, a vessel that is built with Sulfurex. You have a pore in there, but then experience has shown us that with Sulfurex, what happens is that the pore just corrodes open, and then the corrosion stops. So you don't have the issue that I showed in the first picture. Another issue is condensation corrosion. Now, this is the top cover of an HP stripper. Normally, if this top cover is properly insulated, you should have on this liner plate a nice oxide layer cover. But in this case, we see that the oxide layer is only on this part. Now, if this was an austenitic material, what you would see is that if you measure the liner thickness, this part will be much more thinner than the parts that have a little bit of covering. But with this Sulfurex material, you could hardly measure any wall loss, although the material was poorly insulated. So condensation is occurring on the top cover, but not condensation corrosion. I mentioned earlier that in our designs, we eliminate crevices. But sometimes you cannot avoid crevices because when, for example, the gasket is not properly fitted on the top cover of an equipment, you can create a crevice. And then for the austenitic materials, you can have a nasty situation like this, and you need to repair it before you can box up your equipment. For Sulfurex equipment as well, this does happen, but then all you see is this bluish oxide layer on the surface without any attack to the material itself. So the material is much more forgiving, let's say. With chloride stress corrosion cracking as well, by introducing Sulfurex, we've eliminated this. This picture is of an austenitic stainless steel, and the conditions that are required for you to get chloride stress corrosion cracking are listed here, but I'm sure that you are all familiar with this, so this is not anything new for you. Also, I have to point out that in the 20 or so years that we've been building equipment with the Sulfurex material, no Sulfurex HPCC has suffered from chloride stress corrosion cracking. This picture is an unfortunate event that happened for a client. So 8 days after a turnaround, they had to shut down the plant because they had a tube rupture. And what happened? I think during the turnaround, something was left in the stripper tube. And when operation started, this created a block. So you created stagnant conditions, high temperature. The oxygen and CO2 that are supposed to come from the bottom of the tube could not reach this area. So, of course, after just 8 days, the tube ruptured, and then the plant had to be shut down. And this is a tube that is made from an austenitic stainless steel material. How does Sulfurex fare under similar conditions? Now, this is a Sulfurex stripper. You have the same, you have an issue of fouling. And what this means, because you have this deposit of oil and corrosion product over here, you are not getting enough liquid into your tubes, so the tubes are running semi-dry. If you have an austenitic stainless steel material, this would rupture at some point. You cannot run to the next turnaround. But in this case, the plant ran when the plant was shut down for the turnaround. Our inspectors went there, carried out inspections, and the good thing was that when we looked at the distribution of the wall thickness, it was normal as we expect. Because in other situations, you would find out that the tubes which are running dry would have a higher corrosion rate and less wall thickness compared to the tubes which have some liquid in them. And also, you could not, the tubes which were thinner were not related to those which were running dry. You could not make that distinction. And this is another nice example of the performance of Saphorex. This occurs when we replaced our Saphorex stripper in a competitor plant. To be able to do that, the liquid inlet had to be modified. Normally in the Stami Carbon design, the liquid inlet for our strippers are on the side of the vessel. But in this case, we needed to have a central liquid inlet system. What did this mean? This means that the tubes which were actually close to the liquid inlet were being flooded. If you look at this picture over here, the further away the ferrules are from the liquid inlet, you get what is expected of a liquid level and then a gas phase. But the tubes which were closer to the liquid inlet were flooded, so you had liquid going in through the gas outlet and flooding the tubes. But the plant ran for more than 2 years before it was shut down and then opened, and then we carried out inspections, and the flooded tubes were still intact. You cannot have such operation with austenitic stainless steel. And this is another example of where a Saphorex stripper was replaced in a competitor plant, again, because the plant needed an emergency stripper to operate. In this plant, actually, the operating temperature in the stripper is way higher than in the Stami Carbon plants. So initially, there was a discussion, are we comfortable putting Saphorex under such severe conditions? But we believed in our product, so we placed it there. And also, with the condition that every year the plant has to shut down for us to check the performance of the stripper. And once again, whenever we shut down, despite the fact that this picture clearly shows that there was really poor liquid distribution, because these brown tubes have enough liquid and these are running almost dry. But we can see from the distribution again of the tubes that everything was running perfectly. Also, the corrosion rate was good. This is also a vessel with electroslag overlay weld and then the internal bore weld connection. And after 6 years of operation, it looks almost new. There are no visible signs of corrosion. So, let's come to this slide. After 20 years of operation, the main purposes for making Saphorex have been achieved. We've eliminated quite a lot of the corrosion phenomena that are associated with austenitic stainless steels. And when we look at the plant, except from the stripper, we can see that for liner material, for example, the corrosion rate that we measure on Saphorex is almost zero compared to the austenitic stainless steel materials, which is a 316L urea grade and the 2522-2. When it comes to HP strippers, when we compare the passive corrosion rates of Saphorex to the BCO5, we see that they are comparable, which is not something that we or our clients are happy about, but we have never reported any active corrosion. And as I showed before, when you operate plants, upset conditions occur. Tubes can get flooded, tubes can run dry. And in those conditions, the Saphorex shows its strength because it does not go active. You cannot have that with an austenitic stainless steel material. When you are running dry or you have a flooded tube and you don't notice it, it will rupture. But we saw that there is a need for improvement, because we and our partners are always striving for better ways to serve our clients and to improve upon our products. So Stami Carbon from 2011 teamed up again with Sandvik to come up with an improvement on the Saphorex material, but with a few caveats. That we see that apart from the stripper, in the rest of the synthesis section, Saphorex performs excellently. So we want to make improvements, but for a material that will only be for the stripper tubes, so that in that part of the synthesis section as well, we can clearly say that the material is outperforming the austenitic stainless steel materials. So the plan was to come up with a material that has enhanced corrosion resistance at high temperatures, because if you take a look at the synthesis section in a urea plant, the HP stripper is where you have the highest temperatures. And we also wanted to extend the lifetime of the stripper by extending the lifetime of the stripper tubes, and then make this also suitable not only for stomach carbon plants, but for competitor plants, so that when it's time for them to replace their strippers, for example, they can consider stomach carbon technology. And this is important because for our competitor plants, the temperatures in these strippers are significantly higher than we have in stomach carbon technology. So then we began quite a lot of work. So this was quite a busy period for myself and my colleagues. First of all, we thought of a game plan. And that game plan was, for the past 15 or so years, there has been a particular way of thinking about Sulfurex and how it performs and why it performs the way it does. Let's throw all of that out of the window and come up with a new way of thinking. So we created a broad matrix of experimental alloys, but still sticking to the super duplex way of thinking. And then the other thing that we wanted to do differently from what was done in the 90s was that we wanted to test in the exact condition or as close as possible. So for generation 1 of Sulfurex, so the Sulfurex that was developed in the 90s, they developed it using standard tests like Huey test and Stryker test. But we decided that we will take the composition that you find in a stripper tube and recreate it in the laboratory using this titanium autoclave over here, and test our alloys together with Sulfurex, and then choose the composition that outperforms Sulfurex. Second thing is the temperature here is quite high, higher than you would find in a stripper, and also it's zero oxygen. So the conditions that we tested in are much more severe than you'll ever have in your plant. We also wanted to make sure that the material that we come up with will have equal or better mechanical properties than the standard Sulfurex, and also that we will have a good structural stability and weldability. And this is because for duplex stainless steels, the more you try to improve the corrosion resistance, you run the risk of having issues with structural stability, especially when you weld. After a few years of working on it, we are happy to say that we have a new product, which we call Sulfurex Star. And then the first generation of Sulfurex is Sulfurex Infinity. We have a high alloyed duplex stainless steel, so it's in the super duplex grade, just like Sulfurex. It's optimized for carbonate corrosion resistance because we developed it in the same environment. We've maintained the weldability. Actually, nothing changes over here. You can still use the welding consumables for the Sulfurex Infinity. So the welding consumables for Sulfurex Infinity can be used for Sulfurex Star. The mechanical strength is also higher. And since this is being used for heat exchanger tubes for the stripper, it means that for the plugging as well, you can run thinner than normal Sulfurex before plugging, if necessary. And also we achieve the structural stability that we want for making the tube-to-tube sheet welds. There was another thing that we did think about. In materials, properties are related to microstructure. But then the microstructure is also influenced by your production sequence. So we made sure that for the testing coupons that we made, it goes through the same processes that an actual stripper tube will go through before it gets to the client. So we had the same casting, hot forming, cold forming, and heat treatment processes. This is a microstructure from the first casting of this material, which was done in 2016. Between then and now, we have a full production, commercial production of Sulfurex Star. In order to go into full production, of course, the chemical composition and a few things have to be tweaked to improve it and to make it better in line from the laboratory conditions to actual production. And we've optimized the composition, fine-tuned the phase balance, and this supports full-scale production. So now we have products which are included in the ASTM standards for tubes and pipes. We have a UNS number, and since normally the first question that we get is what is the chemical composition, then this is the nominal composition as provided by the UNS number. So when you search this in Google, you will come up with a nominal composition for Saphorex Star. Excuse me. When it comes to the corrosion resistance performance, comparing Saphorex to Saphorex Star, we have achieved at least 20% on the Saphorex, between 10 and 20%. This will increase the lifetime of the stripper. So this value is just in terms of corrosion, but also because the mechanical strength is higher than Saphorex Infinity, it means you can also plug at a thinner wall thickness, which also gives you some extra lifetime. We have conducted field tests at a plant in Austria, and the results are also very excellent over there. And these are some of the standard tests that are carried out on Saphorex, although, let's say, pitting is not an issue that we deal with in urea plants. So this table over here shows the improvements in mechanical strength, both at room temperature and at elevated temperature of 250 degrees. The ductility of the material is also improved despite the high strength. To be able to fully accept this material as a heat exchanger tube material for Saphorex for our strippers, we needed to carry out extra testing as well. So we did the strength of the tube-to-tube sheet weld. So we had a block where the tubes were welded into this block as you would have in a tube sheet of a normal equipment. And then we carried out the pull-out tests. We also did the standard corrosion resistance tests that we specify in our Stami Carbon specification. So the striker tests were also done. We did some macro and microscopic examinations in the heat affected zone and in the weld. We also carried out crack and flow assessments at the equipment manufacturer. We carried out hardness tests. We made ferrite content analysis in the heat affected zone. And then we also, importantly, carried out a homogeneity test, because this is a change in the composition. So we want to make sure that the ferrite austenite balance is equal when you take a full length of a stripper tube. You want to make sure that the austenite ferrite balance does not change along the tube. And of course, before we can commercialize this, we need acceptance by the codes by which we design. And we have a code case approved by ASME in March 2018 with the code case number 2914 for vessels which are also designed according to European standards. We have the TÜV-Nord approval for PMA, particular materials appraisal, for the AD 2000 and for the PED, the Pressure Equipment Directive. The Saphorex Star will only be used as stripper tubes, because if we look at the synthesis section, that was the only place where an improvement was needed for this material. The full-scale tube production is qualified and implemented, so tubes are already being produced in Sandvik, and we are proud to say that we've already sold 3 vessels with this material, and they are under construction by the equipment manufacturers. I mentioned in my second or third slide that there was an issue with crosscut end attack. So again, this is another development that Sandvik and Stami Carbon went into to solve. So there are 2 issues here. When you design a plant with austenitic stainless steel materials, normally you don't have any thoughts on, let's say, ductile brittle transitions when you are talking about sub-zero temperatures. But because we license plants in different parts of the world, when we have clients who are in colder climates, they ask us, hey, now you are selling us a duplex material. What about minimum design metal temperatures? And this became an issue because for large parts made from large forging blocks of Saphorex, then meeting impact values that the clients were specifying became an issue. So to be able to solve this, we sat down and thought, well, this material Saphorex that we have has really good corrosion resistance. How can we improve the mechanical properties at sub-zero temperatures without impacting on the corrosion resistance? And after brainstorming, we realized that, well, properties are related to microstructure. So why don't we try and change the microstructure by changing the way in which we process the material? And so we shifted our focus to powder metallurgy and thought about hot isostatic pressing, which will give us actually a really fine microstructure, because mechanical strength is related to finer microstructure, but still keep the Saphorex chemical composition. By doing so, we also realized that actually the liquid dividers in strippers have this issue of crosscut end attack, where the liquid divider holes grow bigger faster than we expected. And a side effect of going to hipping was that actually we solved this issue. So now we had a product that addresses the issue of minimum design metal temperature at sub-zero temperatures, and also solving a corrosion issue related to liquid dividers. And this is exactly what I'm talking about. When you have a hot isostatically pressed structure, because you start from fine powders which are not more than 500 microns big, you end up with a fine structure like this, which is equal in the X, Y, and Z direction. And this compared to a non-isotropically extruded structure. So assuming that you have a liquid divider where this surface is exposed to ammonium carbonate, what happens is that because austenite is the weaker phase in ammonium carbonate, it starts to corrode, and because the grains are elongated, you get a largening of the liquid divider holes. But if you take this structure, we've eliminated that. That cannot happen over here. And there again, we have code approval from the PET, so we have a PMA, pre-PMA for that. Already a project has been carried out where we had to make the ejector of the plant and a check valve from the HIP material because of the low temperature requirements. We also have ASME approval for this method of production. And the code case is as stated over here. And as you can see, the UNS number for the HIP products is the same as for Saphorex Infinity, because we have not changed the chemical composition. All we did is change the way of production. And for the liquid dividers, these are actually the first liquid dividers in 2012 that we made from the HIP technology. This was placed in a plant in Germany. And in 2014, this picture was taken. You can still see the machining grooves. Last year, I was at the plant myself to check. And again, still, we could not measure any enlargement in the holes. And the client was so impressed because when we placed this in, after a while, he replaced the full set with the old Saphorex. And then when we did inspections, he was seeing that these liquid dividers were staying the same, whilst the old material was deteriorating. And as of now, they've reordered a full set in the HIP liquid dividers because they see how perfectly that this is performing. And this picture is also quite interesting because we did a test in the lab where we placed a HIP part which had been machined. So you see the machining grooves over here. And then again, a wrought part which also has been machined. And after 24 hours in the autoclave, you can actually just see the difference, that this remains the same. And this, because of the structural difference, the cross-cut surface has already started to get attacked. Since it sometimes gets a bit confusing for clients on, they think, well, now you have so many Saphorex products, so what is what? I think this slide helps by using a schematic representation of a HP stripper. If you were supposed to buy a stripper today, this is how it works. So you have the liner material, which is from Saforex Infinity, which is a Saforex that you all know because the liner materials perform excellently. The tubes, which are in orange, will then be Saforex Star because that is the material specifically developed for the process conditions in the HP stripper tubes because temperatures here are much more higher than here. And then for the liquid dividers, which are in blue, you would have Saforex Degree, which is the same as Saforex Infinity, but just that this is produced from powder metallurgy. And for Saforex Degree, you can have liquid dividers, radar cones, and then large forgings made from this. So in conclusion, with Saforex Star, we have a material that we believe the improvement, which I talked about. And finally, when you use Saforex, it gives you more flexibility to operate your plant because the material is much more forgiving. I did not mention it earlier on, but actually in a case, the plant lost oxygen passivation for more than 2 weeks. And they didn't have to shut down. When they opened the stripper later on to check, because the stripper is the most critical equipment in this case, it was fine. So we also have a plant that runs at 0.1 volume % oxygen, and also there are no issues. So you have an advantage on your turn down ratio. And another thing is that when you operate a plant with Saforex, the requirement to block in for only 72 hours is removed. So now you don't have a blocking in time period restriction. Of course, you have less inspections and longer inspection intervals. And yeah, this I talked about already. And so you have safer operations and higher yields. So thank you very much for your attention. And if you have any questions, I'm happy to oblige. Yeah. No. So when you have material in the liquid phase like 2RE69, when it is corroding, it is an intercrystalline process. So the grains get corroded out, they fall out, and then that leads to the roughening of the surface. That is how the liner plates corrode. But when we take a look at Saforex liner plates, all that we see is that after the first time you open it, the surface is slightly etched, and that is it. When we measure the wall thickness, we get corrosion rates of about 0.01, which is even lower than the accuracy of the equipment that you are measuring with. So it's almost zero. But after 20 years of operating with 2RE69, you will measure some wall loss because the grains fall out, and then you get this rough surface that you are talking about. So the rough surface is to be expected because that is how the material corrodes. So it's not just in your plant. We do see it in other plants as well. So after a time, when the liner plates becomes too thin, you have to reline. Yeah.
I will ask you, but I think my question is very long and the story of these strippers. We have old stripper, we replaced this stripper, but we have problems with these strippers. May I would ask you, because we have many reports from the carpenter, so if I can ask you later.
Yeah, that is fine. Yeah. Yeah, we can discuss later since it's a very specific question. Yeah.
Thank you.
Yeah. Of course.
Hello all, myself Rahul Patel. As Rule introduced me, I'm a process engineer, so my presentation will be mainly focused on the process aspects. The presentation is about improving the energy efficiencies of urea plants, how the things evolved over the decades till the current technology. The current technology is the ultra-low energy efficient technology, which has been implemented in 2 of our grassroots plants under construction in China, but it is also available for revamping the existing plants with all conventional or CO2 stripping technologies. We'll look at some brief history, the innovations in urea technology related to energy efficiency, also operations. The first, which was the main innovation done by Stomach Carbon or DSM, was the use of passivation air in urea synthesis to allow stainless steel, so 316L, to be able to use in urea synthesis. This is what Kirk told. The second one is CO2 stripping technology, which was invented by a Dutch scientist. His name is Mr. Kaas en Brood, which literally translation mean Mr. Cheese and Bread, followed by pull condenser, pull reactor technologies in 1996, so about 25 years ago, which is the state-of-art technology still implemented in urea plants. There are some other improvements like putting the reactor on the ground floor to reduce the capital expenditure of the civil structure. That's an oven core concept. All these innovations were driven more for improving the safety of the plant, also reducing the capex, the opex, the emissions, ultimately reducing the total cost of the ownership for the plant. These are the 2 recent developments in the urea melt industry. The first one is adiabatic flash technology, which is a lower capex, lower opex technology. And the second one is the ultra low energy technology, which is very low energy consumption, but equivalent capex to the urea 2000 plus technique. These 2 will be elaborated more during the presentation. Before we continuing, let's look at the basic chemistry of the urea plant. I'm sure most of you know this, but I want to emphasize on how the chemistry is. The ammonia and CO2, they are the raw materials. Ammonia is basic, CO2 is acidic. The acid and base react and form a salt, which is ammonium carbamate. This reaction is highly exothermic. This salt is corrosive in nature. That's why we have developed the Sulfur X materials. The further dehydration of the salt leads to urea and water. This is mildly endothermic reaction. The overall reaction from raw material to urea is an exothermic reaction. So urea plant itself has a total, let's say there is an overall exothermic heat output. This is a basic or traditional conventional urea flow diagram, urea plant flow diagram, where a single piece of high pressure equipment was used. This is in 1950s, 60s, the very first urea plants built with the very small capacities. The synthesis was operated with 200 bar, 190 degrees C, very high NC. There was no stripper in those plants. The dissociation of carbamate was done mainly in the MP and LP sections with the use of steam. In those plants, there was also the prilling tower. So no granulation technology was present those days. The energy consumption of these plants were very high, about 2,000 kg per ton, which is almost 3 times from the current standards. They had a very high HC ratio in the synthesis because all the carbamate dissociation was done at medium pressure and low pressure conditions. These are some of the plants from 1950s and 60s, which utilizes the conventional stomach carbon technology. That's the first one, the first stomach carbon urea plant, built with 70 metric tons per day, which is factor 50 smaller than the current standard. This is the energy flow diagram for the conventional technique. The steam was used only once in the urea plant. So the steam from battery limit was used either to do dissociation in medium pressure or at low pressure or evaporation. The heat was lost ultimately in the cooling water. This was a highly inefficient process, required about 2,000 metric tons per day of 2,000 kg of steam per ton urea. In 1967, Mr. Casabrook invented the CO2 stripping technique, which allowed reduction in energy consumption for the urea plant. In that process, in the high pressure synthesis, two heat exchangers were introduced. First, the stripper and high pressure carbamate condenser. Steam was consumed on the stripper to dissociate the carbamate and condensed in the stripper. So one step back. That's the stripper where the steam was consumed, the medium pressure steam. And the vapors produced after dissociations were condensed in the HPCC, resulting in LP steam production. This LP steam was used, most of it within the urea plant, and surplus is exported to battery limit. As this resulted in a recycle at high pressure, the H2C ratio were much favorable compared to the conventional technology. So the high pressure recycle, that's the high pressure loop. So the recycle of the gas was almost water free. The energy consumption of these plants were about 900 kg per ton. This process was called N is equal to 2. So the heat was used within the plant 2 times. The steam was used first over the stripper. The vapors which were condensed in the HPCC, resulting in LP steam. Those LP steam was used in the recirculation as well as in the evaporation section as main consumers. These are some of the plants which utilizes the HPCC-based CO2 stripping technology built in 1990s. They still had a very high footprint because the vertical reactor was the only reaction zone. So the height-wise, they were very high compared to the current technology. In 1990s, the pull condenser was invented. That's the most successful urea technology so far by stomach carbon, where there were not directly the energy efficiency improvements were gained, but more operational improvements were brought into picture. The pull condenser provides a heat exchange along with the reaction in one vessel. What is exactly the pull condensation? The pull condensation is a pull of liquid sparse with immense quantity of gases. So it creates sufficient turbulence to provide high heat transfer as well as mass transfer coefficients. Those are very important to reduce the heat exchanger sizes. So the use of pool condenser actually resulted in a smaller bundle requirement compared to HPCCs. And as this is a horizontal vessel, the vertical footprint of the urea plant was reduced. The operational benefit of pool condensation were also quite significant. So what you see here is on the y-axis, the synthesis pressure during the startup with the time. Most of you who operate HPCC plant know this behavior. So when you start the startup, the urea plant, so here you start injection of ammonia. After a certain moment, injection of CO2. The pressure keeps building up. Once you start condensing in HPCC, there is a slight dip. And here is the time when you open the liquid supply from the reactor to the stripper, which is a term called reactor overflow. There is a sudden increase in the reactor pressure. That's the inverse response of the process. As the stripper responds very fast, but the HPCC could not cope with it because it was a falling film condenser, which has a much higher response time. So there was a sudden increase in the pressure in those concepts. But when you do the startup with a pool condenser or pool reactor, the inverse response was almost fully eliminated. So you see a very smooth pressure increase without a sudden increase as soon as you start the reactor overflow. This was the main improvements in terms of operational flexibility. Apart from that, the pool condenser also provides a much larger operating windows for NCs. In HPCC plants, if the N to C ratio in synthesis deviate from 3, so if it goes to 3.2 or 2.8, you get a very difficult situation to handle the pressure in synthesis. In pool condenser, pool reactor plants, it is much flexible. So within 2.5 and 3.5, the synthesis can still handle these NC changes. In 1994, Mr. Case Yonkers invented the pool reactor, where he combined the vertical reactor and the pool condenser together in one vessel. So this is a one vessel which does the heat exchange as well as complete reaction. This is the concept which is useful till 2,600 metric tons per day. So most of the new urea plants, they have a pool reactor till the capacity of 2,600, 700 metric tons per day, as it provides the heat exchange as well as full reaction. These are some of the examples of pool condenser plants. That's one of the largest running, 3,500 metric tons per day, Yaroslav scale, and has also achieved more than 4,000 metric tons per day capacity during the capacity test, load test. These are some of the pool reactor plants, which are built till about 2,600 or 700 metric tons per day. The capacity is mainly limited due to transportation limits. How did the elevation change in all these different concepts? These are somewhere in 1960s and 70s in between time. The first generation CO2 stripping process. The vertical footprint was very high. The plants were as high as 74 meters. The pool condenser, pool reactor plants, They have a height of about 42 meters max. And these are the most favorable. The OMAN core is the most favorable concept nowadays for large capacities as well, with the maximum 25 meters height. These are not, the heights directly benefits on the capex because the civil structure cost goes down. So these are not really resulting in energy improvement, but they are more on the capex. To improve the energy efficiency from Urea 2000 plus concept, we did some development. We consider Urea 2000 plus as the benchmark for those developments, as it has been licensed for more than 40 plants. Extreme operability, it has a high reliability. It utilizes the steam consumption of 868 for a prilling plant. The prilling plant is the most energy intensive comparing a granulation. So if the prilling plant has this number, the granulation will be lower than that if you use granulation. As the typical pool condenser plant. To reduce the energy, we identified the very simple possibility with an inline medium pressure flash. So only flashing the liquid which is coming from the stripper, normally going to the rectifying column, now flashed at an intermediate pressure. We optimize this intermediate pressure based on to gain the max energy benefits. So the intermediate pressure is in between 20 and 25 bar. That's where you gain the most benefits. The vapors generated in the flash are used to perform a pre-evaporation job. Why is it called pre-evaporation? Because the urea solution is concentrated from typical 72 to 78%. So it's not doing the full evaporation, it's only doing a part of evaporation. So it's a pre-evaporation. After the pre-evaporation, the urea solution is sent back to the tank, and the further evaporation can be done as it was done in the other techniques with the use of steam. The carbamate which is formed in this pre-evaporator cum medium pressure carbamate condenser is of course separated from the gases first and sent back to the synthesis. The vapors are sent to the 4-bar absorber for further washing. When we have this MPCC pre-evaporator available, we thought of taking a step further and eliminating the HP scrubber and the ejector, because the job of HP scrubber and ejector can be performed directly by this medium pressure carbamate condenser cum pre-evaporator. So it reduces the two high pressure piece of equipment and also gives you a benefit on the energy consumption. This technology is known as launch melt flash design. It's successfully running in 2 of American projects, so since last 1.5 to 2 years. Is also implemented in a revamp in China, where they got significant benefits from it. Again, to highlight what are the benefits of it, you save the steam of about 150 kg per ton compared to a traditional Urea 2000 plus process. There is a lower capex because the HP scrubber is eliminated, HP ejector is eliminated, and the high pressure pipings are eliminated. To go further, we developed a concept which is there at the booth, ultra-low energy design. During the development, it was also known as 5XX. So the aim was to be in the figures of 500s. That was already a prerequisite if you want to make a concept. And we further developed and reach our target. So there is a concept which results in the figures of 5XX. This concept nowadays is known as ultra-low energy design because in case you have a very high quality steam, you can actually get even lower than 5XX, it could be 4XX. But just to avoid that misinterpretation, we call it ultra-low energy design. To understand it better, I recap the traditional urea 2000 plus process energy flow diagram. N is equal to 2 process. Steam is used first in the synthesis. Low pressure steam generated in the HPCC or pool condenser is used to do the dissociation at LP stage and the evaporation. In N is equal to 3 process, the heat which is brought to synthesis is used 3 times. First, at a high pressure stripper. Second, at an intermediate stage to do dissociation, medium pressure level. Third, it is used to do the evaporation, the full evaporation, not pre-evaporation. The target was to do the complete first stage evaporation. How is this conceptualized? You see 2 pieces of high pressure equipment, so it's a full reactor concept, applicable to 2,600 or 1,700 metric tons per day. It has 2 bundles. The upper one is steam bundle and the lower one is carbamate bundle. A typical stripper, as in the traditional process, is used. The liquid from the stripper is flashed at medium pressure condition, similar to the concept I mentioned before. So there is a flash at medium pressure condition at about 25 bar. But the liquid from that flash is heated up over the carbamate bundle. That's the next step. So the carbamate is dissociated over the carbamate bundle. The vapors which are generated during the dissociation are condensed along with the flashed vapors and the off gas of pool reactor over a MPCC come first stage evaporator. So it's not pre-evaporator, it's a first stage evaporator doing the full first stage evaporation job. Because the first stage evaporation is typically the most LP steam user. So it requires the majority of LPCC is used on the first stage evaporator normally. So the urea solution is introduced from the top to flow through the tubes. So it's a falling film first stage evaporator. After the condensation, the vapors which are still left, they are washed first with the low pressure carbamate, and the remaining is sent to the back end for further cleaning. The carbamate formed is sent to the synthesis with the use of high pressure pump. So this concept still has 2 pieces of high pressure equipments, but a complete new medium pressure section. The energy consumption of First, what does this concept utilize? It utilizes the CO2 stripping. So CO2 stripping is still used. It utilizes the pool condensation, which provides the significant operational benefit. It's still there in the concept. It is a low elevation concept, so even for the larger capacities, the vertical reactor can be placed on the ground. It has a limited HP equipment, which because the HP scrubber and the ejectors are eliminated. There is a direct heat exchange between the synthesis and the medium pressure carbamate flowing through the bundle, so there is no extra heat medium introduced. It is also implemented with the sulfur X material. The medium pressure conditions which are used are well proven in the conventional technology, but also in the different revamp option we had done in past. So there is nothing new in that sense. The operating conditions are similar, but the main thing is now the heat is integrated from synthesis to medium pressure directly. The overall benefit of this concept is, with that basis of design and that steam quality, 558 kg per ton of urea for a prilling plant. So if you have granulation, it would be always lower. Summary of the concept: it utilizes the steam, 558 kg per ton, 23 bar steam, 330 degrees C. This is the typical extraction steam from the turbine. This utilizes the maximum proven technologies: falling film, pool condensation, the known pressure levels. As it has a pool condensation, the ease of operation and reliability is retained. The introduction of complete new empty section and elimination of high pressure scrubber and ejector is balanced out in terms of capex. So the capex is equivalent to the benchmark Urea 2000 plus technique. These are two grassroots which implemented. One is implemented last year and this one this year. They are under construction and to be expected running in 2021. They are both in China because the energy efficiency in China is taken very important nowadays. So all Chinese plants, they look for high energy efficient technology. But this technique is also available for revamping your existing plants. To conclude, Stammy Carbon is a leading technology company, innovating since 1960s. The latest technology for melt plants results in the lowest total cost of ownership. Thank you. This is about to discuss what are your needs and concerns related to energy, but also emissions, operations, all the needs you have. Yeah, go ahead. Yeah, that's one. I go back. Yeah. So one step back. Yes.
This is the normal work which we have.
Yes, Urea 2000 plus.
But in new modification, can you now transfer to a new modification for you when you delete the scrubber?
Correct.
These scrubbers we have vent to control the sense pressure, but this vent not mentioned here on the board condenser.
So what happens is when you delete
board.
it, your vent from synthesis is controlled by a control valve.
So we have.
Yes, you will have a control valve, a new control valve, which will be much bigger, of course, than the traditional one, because it has to have a much higher flows now, going to the medium pressure stage.
Okay, so this vent will not delete it.
There will
For
be
controlling.
another vent, a bigger vent needed.
So, okay, thank you.
A vent directly from the reactor.
Yeah. Direct.
Yeah.
Okay, thank you.
Okay.
Thank you for the nice presentation. What is the maximum plant capacity you can design as a STEMI carbon?
For ultra-low energy technology
For
or in general?
in general, for
In
the
general.
granulation system.
I know there are prospects of 5,000 metric tons per day, which STEMI carbon is aiming for. I think there is no real limit on the capacity. If you have a requirement, STEMI carbon can see how it can be implemented. So it's more, there is no, let's say, fixed answer to the upper limit.
So far, what is the plant, the maximum?
Running capacity.
Yeah, the running.
The one I mentioned, slough scale, was running, or the load test was done for capacity more than 4,000 metric tons per day. So that is the maximum running capacity, apart from 2 American clients, CFIs, which are also running more than 4,000. Is that correct, Arik? Know that? Yeah. So they are the large ones which are running.
Okay, thank you.
Hello all, I'm back. This presentation is about an incident happened in one of STEMI carbon urea plants in Canada, where a reactor corrosion occurred during a synthesis block-in condition because of loss of passivation during the block-in. So there were some undesirable conditions which occurred during block-in, were not noticed, ultimately resulting in a loss of passivation in the reactor. So there was a case study done, and that case study will be presented here. The content of this presentation is, first I'll show the process flow diagram, the timeline, what actually happened during the block-in, based on the DCS data, then the observations from the field, but also during the inspection. How did they find out the cause of this? So there was a cause identification methodology used. Some mechanisms were derived theoretically, and later on in a detailed case study, they were validated with some numbers, some calculations behind it. At the end, there was a recommendation given based on this study to do and not to do during the block-in conditions. Thus, the PFD, only for synthesis, is the typical HPCC plant. CO2 stripping technology, N is equal to 2 technology, so heat is used 2 times. The equipments in this plant, the vertical reactor was made from 316L urea grade, so BCO1 material. This is the data from DCS between 2 runs, first run, second run, and block-in. This was the first run on 3rd of July 2013, somewhere here. The first run occurred. You see the temperatures are rising. These are the temperatures in the reactor. So green is the head temperature, so overhead vapors. So highest temperature in the reactor. The red is the bottom of the reactor, where the lowest temperatures are normally. So the temperatures increased, everything was normal. The product quality was normal. But due to some rotating equipment failure, they have to do a block-in. So the block-in starts here. They did block-in. The temperatures, typically during block-in, they go down because of the heat loss and some heat required for further urea conversion till the equilibrium. That's common. The temperatures dropping, and then there was a point when the temperature start to increase. These were not noticed on the DCS until the actual incident occurred of loss of passivation. So nobody cared about it. The temperatures increased, stabilized to a conditions much higher than what you have normally. So this is something like 174 degrees C, 90 bar conditions in synthesis. They restarted the plant. So that's the second run. You see, they run it till about 22 hours. At the start, they had not the usual color of the product, but very brownish. And after about 22 hours, so this is almost 1 day, they had a leak in the reactor. Due to that, they have to stop production, drain then the synthesis, and look for the problem. So what actually happened was, yes, normal colored product during the first run. That was the first run. And brownish colored product during the second run. So, sorry. That's here. And in between was the block 10. So they observed a leak and identified by the leak detection system, and they opened the reactor for the inspection. This is what they saw inside the reactor vessel. This is one of the top tray of the reactor. This is a tall vertical reactor with 10 trays in it, because it's an HPCC plant. There is a sharp interface at the gas and liquid levels, which is about 80% of the reactor level. This is what they saw when they opened it. What is this actually? This is a normal color you should have, and this is the gray color, which is a loss of passivation. So it has no layer. To look in the other equipment, they also opened the stripper. There they do not find any active corrosion, so the equipment was intact. The layer was intact, as it should be. So to do the further investigation, they concluded that something must have occurred during the block-in period, and do the further investigation. The block-in period was 22 hours with this BCO1 material, so 316L urea grade. The maximum allowed is 72 hours, as presented. So this 22 hours was the time to look at what went wrong. This is a cause identification diagram. So what they saw was when they blocked in, they first pulled CO2 and oxygen. And after 9 minutes, they pulled ammonia. So there was like 9 minutes of time when there was no oxygen going along with the CO2 to the synthesis. That's one thing. They had recently replaced their HPV. That's the control valve in the outlet of CO2 compressor to the stripper. So they suspect also that this possible leak through it because the temperatures were increasing. The theory was that there was an extra ammonia, there was CO2 leakage, the carbon generation occurred, and the heat provided by the CO2 was sufficient to strip out the oxygen which was dissolved in the liquid. So the oxygen was depleted in the liquid phase, leading to loss of passivation. So it was a combination. There was stronger acid due to higher temperature and extra CO2, higher temperature itself, and the oxygen was depleted. This was based on the theoretical analysis. These were the points they wanted to look further. Ultimately, due to this, they had their production goal impacted. So they wanted to make sure they identified correct. So based on that theory, the two main causes were CO2 was leaking during the block-in to synthesis, and the CO2 was pulled about 9 minutes before ammonia. So there was no oxygen supply to the reactor or to synthesis during that time. As an operating procedure, Stomach Carbon recommends to stop operation if there is no oxygen supply for 15 minutes of time. So they were still within the limit. It was because it was only 9 minutes. So that could not be the main cause of the problem, although there is some equilibrium compromise because of loss of 9 minutes oxygen supply, along with CO2. So the mechanisms, the mechanisms identified, mentioned before, theoretically, are high temperatures, stronger acid, lower oxygen in the liquid. So they decided to do further case study, look into more detail, and also validate with the calculations. Okay, the first thing they did was to compare a typical block-in temperature profile against, in that particular case. So this is a typical block-in profile. What we see is the temperatures. So by the way, these are in Fahrenheit because it's from Canada. 300 Fahrenheit is about 149 degrees. It's somewhere here. And the highest temperature, 348, is 174 degrees C. So about that. This is a typical block-in period. The temperatures in the reactor, they drop. It's normal. To an extent about 130 or 140 degrees C. That should be 270, about that. That's the typical block-in temperatures. In this particular case, for first few hours, it was normal, and then suddenly the temperatures kept on increasing. The top one is the bottom part of the reactor, and this one is the top part of the reactor. So the bottom part of a reactor heated up faster than the top part. You see the ammonia pulled out. That was about, this is that 9 minutes of time when the CO2 was pulled. There was no oxygen supply along with CO2. The ammonia was continued. The temperature increase during this time was about 20 degrees C, which is completely abnormal. So, what actually happened? CO2 leaked during this time for about 4 hours. But why only 4 hours? Why did it stop afterwards? Because there was no action done. So there was further investigation, checking. So this was typical, specific. Yes, let's look at, so they wanted to check if there was a heat input during that block-in. Was the stripper still having heat supply? Similar to HPCC, the HPCC can also work as a heat source if its LP steam pressures are elevated high enough. They looked at it. They did not find, no, there was no heat supply from the stripper, neither from the HPCC. That was the suspicious time frame of 4 hours when the temperatures increase. Now they look at closely the synthesis pressure, which is the pink line. Is that correct? Yes. That's the synthesis pressure. That's the pressure of the compressor discharge. So the compressor was running during the block-in time. You see, when the synthesis pressure dropped below the compressor pressure, the temperature in synthesis, they kept on increasing. So there was something going from compressor to the synthesis. This theory was further clarified when they looked at the top temperature of the stripper, the off-gas temperature of the stripper going to HPCC and ultimately to the reactor. They saw during that time there was a dip in the temperature. This is a fully traced line. So when there is no flow, it should have a fixed temperature. But during that period, the temperature was decreasing. So there must be something flowing through it. So the theory became stronger by looking at that the pressure of synthesis was lower compared to the compressor, and there was a dip in the temperature in the off gas of the stripper. And you see, after a period, the synthesis pressure increased, equalizes the compressor pressure, and then the temperature increase in synthesis was plateaued. It was no more going up because the compressor pressure and the synthesis pressure equalized, so you cannot send any more CO2 to the synthesis. To verify this theory, the calculations were done by stomach carbon to see if the theory makes sense. These were the main assumptions or inputs. The reactor with the capacity of 121 cubic meter, which corresponds to a urea plant capacity of about 1,100 metric tons per day. The temperature in the reactor at the start were 155 degrees C, 80 bar, and they increased by 20 degrees during this block-in. The addition of ammonia, that 9 minutes extra supply of ammonia, along with the flushing done on the HP scrubber, 20 ton, and CO2 leak estimated as 8 tons, the total heat input matched to about 20 degrees C. So the theory of that CO2 leaking combined with the flush water, combined with the fresh ammonia supply of 9 minutes, together they proved to be 20 degrees temperature increase in the reactor. So the conclusions, what happened? The CO2 addition to synthesis stripped the dissolved oxygen from the reactor liquid. That's happened. The liquid in the reactor was heated up by about 20 degrees C. And this higher temperature, more CO2 means less NC, leading to more acidic conditions. So this combination resulted in loss of passivation during blocking in. Despite of this, we should highlight that during that blocking in CO2 leak, there was still oxygen of 0.6 volume%. But this was not sufficient to passivate under those circumstances. These are the recommendations based on the case study. Actively monitor the temperature in synthesis. If it's higher than 11 degrees C, find the root cause, otherwise stop the plant, drain it. Assure a positive isolation of all feeds, so CO2, but also ammonia going to the synthesis. Do not only rely on the control valves and XPVs, also use the manual valves which are there. Undesirable heat source, stripper, as well as HPCC should be properly monitored. And one should make sure that they have a baseline for the metal analysis. This is about the product. So the nickel in the final product. You should properly measure them and make a baseline for your plant. If it deviates from it, you have to identify the root cause of it. So that is highly recommended to make a baseline for your plant. By the way, these recommendations, including the baseline, they are very important in BCO1, BCO5 plant. So stainless steel urea grade. But we also recommend the baseline in the Sulfurex. Is that correct, sir? The baseline? Yeah. This is still a very important part. Thank you. Your questions?
CO2 side or OMAN side, which better? Because reactor bottom is around 170 degrees centigrade, and plant top 170. So some are telling this is CO2 side or ammonia side, which better?
Which case?
No, sometimes it's if any disturbing. Sometimes people are advising CO2 side. Or I'm not sure about that point, but I need your advice. We are trying to make stimulate.
From stomach carbon point of view, we do not recommend one of the either ammonia side or CO2 side. It's
not for a long time, but momently. No, I mean not for a long time. If any disturbing operation, sometimes ammonia is raised up or CO2. Which, in your opinion, which will be we can go more? Ammonia side or CO2 side? Any effective or?
There is no correct preference. As long as you have sufficient passivation, required.
Yes.
And you're within the operating boundaries. I do not know any preference.
Yes. No, yeah, ratio. We are trying to maintain ratio, but sometimes it's going ammonia side or CO2 side. So no any effective for this reactor or process. I think physics.
Let me elaborate on it. When you talk about the operation, so which side is easy to handle? Ammonia-rich side is easy to handle. Then, in terms of operation, so if you have a more CO2-rich conditions, you will quickly end up going towards blowing a PSV in synthesis compared to the other side. So that's mainly from operation point of view. When you talk about the materials and corrosion, there is no preference on left or right. Yeah, it's clear.
So, my second presentation of the day is about minimizing risks of catastrophic failure in urea plant process lines. Requires RBI methodologies. I think this is an apt topic because from yesterday we've been talking about how to monitor our equipment in the plants, but you realize that most of the discussion has been about static equipment and rotating equipment, but we've talked very less about the pipelines which are in the plants. To cover this, I will begin with the introduction and explain why we need to monitor the pipelines, the importance of it, and the, let's say, systematic approach that we can use to achieve this. I'll also use some case histories to further buttress this point, and then talk about what we mean in STAMI Carbon when we talk about the RBI approach. I'll also then point out how you can achieve this with some inspection strategies, and also point out that it's not all about inspection, but also there are a few things you can do when you are running the plant to further mitigate risks to process lines, and then finish off with the conclusions. We know from history that when we hear of catastrophic failures in urea plants, more often than not, these occur in the process lines much more than in the static equipment. And this does not just happen out of thin air. There are a few reasons why this happens. Now, every plant operates on some sort of inspection philosophy. It's either a periodic-based philosophy where every X number of years the plant is shut down, You bring in inspectors to come and check the mechanical and corrosion integrity of your equipment. Or it can also be condition-based, as we were discussing yesterday. But for some reason, when this happens, we hardly take a look at our process lines, whether from the outside or from internal. So, of course, because whatever goes into your equipment has to pass first through the process lines before ending up in the equipment, whatever damage that can occur to the equipment, your pipelines are also prone to that. Because actually, when we look at the corrosion barrier or the stainless steel alloys that we put in the static equipment to protect them, it's the same material that is used to construct also the pipelines. So the risks are quite similar. And also, number two, the process conditions in the pipelines, temperature, pressure, concentrations of corrosion products are very similar. The reason why sometimes pipelines are, let's say, left in the background is that right from the period of design of the plant, construction, operation, inspections, repairs, modifications until decommissioning, pipelines go through the responsibilities of different people. And so the actual, let's say, group or department who is responsible for a specific pipeline or a group of pipelines becomes diffuse at some point. You also take pipelines, there is something special about them. You have kilometers of them in your plant. So even if you are thinking of, well, I want to inspect them, where do you start? I mean, during your turnaround, do you strip off all insulation and then check every inch of the pipelines? That is virtually impossible. Pipelines also cross battery limits in your plant. So when they cross a battery limit, actually which plant is responsible for which part of the pipeline? And then, of course, the last part is obvious, that unlike equipment where you can relatively easily open the equipment, get someone to go in there and then take pictures, take a look, make measurements, it's not so easy with pipelines. So all of this makes them actually very vulnerable, and to overcome this, we need to have, let's say, a systematic approach that will help us to inspect pipelines and then maintain their integrity. And this is more so important for older plants, because if you have a plant that is more than 15 years old and you've never taken a look at the pipelines, you are actually running a risk. You will never do that with your static equipment. So if the process conditions are similar, the materials of construction are similar, then you should also not do that to your pipelines. And I talked about having a systematic approach, and one of these is using a risk-based inspection methodology, or more commonly referred to as RBI. When you talk about RBI, what exactly is it that you are referring to? You can read whole books on this, but just to summarize this, when you are using RBI, what you are trying to do is you are using risk as a method to prioritize and manage your inspection effort so that you can manage the resources that you have available for your inspection. So basically what you are trying to do with this is to also save time and money. So when you use the RBI method, you are going to rank, this applies also to equipment, but since this is about piping, I'm going to focus more on piping. You are going to use risk as a basis to rank your piping by dividing them into sections, looking at the material of construction, looking at the process conditions, and then the piping with the highest risk ranking. You have to make an inspection plan for them and see how you're going to determine what failure modes can affect them, how to determine the failure modes, and then how to mitigate them. As I go further, I will explain more, but you have to do this both from the atmospheric threats and also from threats which can happen internally. To have a very robust RBI program, you have to involve all stakeholders, And what does this mean? This means that it is not only the headache of the inspection department. You need production, you need engineering, and that includes civil works and piping. You also need your purchasing department, since you're going to be purchasing things from external parties. And most importantly, you also need your third-party contractors, the people who will be building scaffolding, those who will be removing insulation material and jacketing, people who will be doing painting on pipelines. It's important that you include them in the team because they need to understand why you've asked them to do certain things, and they need to understand why they need to do it in a certain way. Because just by having them there and giving them an instruction without any clear understanding can actually lead to more problems. And to have, let's say, a functioning RBI system, any lessons that are learned during your inspection phase should be fed back into the system. So you have what we call like a plan, do. So you have what you call a plan, do, study, act cycle. This part is very important, and I will stress on it further. It can mean two things. It can mean that when you are running the plant and then you have an upset condition, something should be triggered that this upset condition should be put into the system to see if the integrity of any pipeline has been affected. And if it's affected, how do we check it and correct it? Doesn't mean that the inspection interval of a particular group of pipelines has to be brought forward. Doesn't mean that we maintain the inspection interval and then when we are inspecting, we check for a new method of failure. So these things are quite important to be able to run a robust RBI program. And this picture over here is a failed carbon steel pipe. It supplies CO2, and it failed as a result of atmospheric crater type attack. To further impress upon this point, I will go through 4 code cases and how these cases helped the plant to, let's say, rethink about how to incorporate or how to operate a better RBI system. And in most of these cases, the plants didn't even have a running RBI system for their pipelines. So this is the first case. In this case, the failure occurred in the line that runs from the top of the reactor to the scrubber. We learned from the plant that before this rupture occurred, they had on several locations an upset condition. And during this upset, they had the deposit of a hard white crystalline substance in the equipment and also in the pipeline. So after each event, they will clean the equipment and the pipeline with steam condensate and then inspect the equipment, but then actually the pipeline was not further investigated. So, well, what happened is that unfortunately the pipe ruptured, but on the fortunate side, there were no injuries or fatalities. And this is a picture here of the contamination that entered the pipeline. When these events occur, of course, the most important thing is that you have to do a root cause analysis. Then you can learn from what happened to prevent it from being repeated again. What the microstructural analysis revealed was that this crack actually originated from inside the pipe and then led to a through-wall crack, which then resulted in the rupture. The investigations also of the cracks reveal that it is of a stress corrosion nature. And normally, when you have austenitic materials and then you see stress corrosion cracking, you are thinking, okay, is it chlorides? But you will bear with me that we try as much as possible to keep chlorides out of the synthesis section. The materials were investigated. By that I mean the crack surface was investigated, and we didn't find any chloride contamination. But the lesson here is that actually, when you have offset conditions, you should incorporate this into your risk-based inspection system if you have one. Even if you do not have one and you have an offset conditions where your piping is affected, you should try to figure out, one, what was the contamination product? Will it have any effect on the piping? And if it will have any effect, how can we further mitigate it? And if you have a running RBI system, this should be fed into the system to determine how it will affect the risk ranking of the pipeline or particular set of pipelines that have been affected. In the second case, this happened actually in the drain lines. If the process lines are, let's say, forgotten about, then the drain lines are actually at the total bottom of the list of priorities. What happened was that the clients realized that there was a leaking drain valve that connects the scrubber to the drain system. For several times, they tried to, so every shutdown, they tried to repair it, but then it doesn't work. The leak continues. And then as a workaround, they decided to overpressurize the drain lines compared to the synthesis section to prevent the valve from leaking. You have to bear in mind also that these drain lines are traced. The drain lines were not drained after every, let's say, every 12 hours. They were not drained, so it was just kept in. Unfortunately, this overpressurization didn't work. So what happened was that this valve was still leaking synthesis product into the drain lines. The drain lines were made of a lower material quality than the synthesis lines. So you had two things occurring. You have a stagnant condition, and then you have high temperature. Because actually, because these drain lines are traced, you had the tracing line directly in contact with the drain line without any spacers in between. So you had really high temperatures, and this led to a wall thinning. You can see the part where the drain line is in touch with the tracing line. You can clearly see the difference in wall thickness between here and here. And so it's no surprise that as a result of the high pressure, carbonate, stagnant conditions, you get a rupture at some point. So here again, we have a few learning issues, both from the client side and actually also from STAMI Carbon. You should not just think of your process lines when you're thinking about RBI for your piping system. You should also think about the drain lines. What the clients then did was that they decided to then upgrade these drain lines from 316L material to actually Saphorex. So they decided to construct the drain lines from Saphorex. In STAMI Carbon, we also made a new recommendation for the material of construction of drain lines, and we upgraded them from austenitic materials to the duplex grade. Not necessarily Saphorex, but to a duplex grade, which is much more resistant. And this is a very important point, that when you are tracing lines, you should always have spacers between the tracing line and, of course, your process line. Apart from the heat as well, if you have any leak in your tracing line, this could also have an impact on your process line. So it's an important point. This is the third case, and this case occurred on the reactor outlet line to the top of the stripper. There is a weld outlet on this line. This plant had been running for 25 years. No attention has been paid to any of the process lines. But 2 weeks before a plant turnaround, it was realized that this weld outlet for the thermal well was leaking at this point. There's a weld over here. And to avoid stopping the plant before the 2 weeks, it was decided to repair this weld on stream. Unfortunately, when they were repairing the weld, this weldolette ruptured, leading to several fatalities, which is quite unfortunate. Then we had to do a root cause analysis. Why did this happen? And a few things jumped out. So first of all, by doing a microstructure analysis of the failed weldolette, we could see that you had some corrosion in the heat-affected zone. It was intergranular in nature. The second thing was that actually the material of construction for the weldolette was not what was specified by Stami Carbon. This was a normal 316L urea grade material with 15.3% chromium, which is quite low. Stami Carbon recommends 316L urea grade at that time because this is an old plant, and that has minimum 17% of chromium. So that already is an issue. What this triggered is that the plant now had to check for all the other weldolettes they have in the synthesis section, that do they have the correct material of construction. The other thing is that actually you do not need to have your plant off-stream to be able to do something like this. You can actually do on-stream X-rays. And you have to bear in mind that when you do this, you are not looking for cracks, because that can be quite tricky depending on the orientation. But you are looking for loss of material, which will be evidenced by the shading that you will get based on the density. So you can actually detect on-stream whether you have a problem with your weldolettes. Also, include PMI checks in service. This could also be done. Your plant doesn't need to be offline to do that. But this is an important point, not only for running plants, but also during the construction phase. Because more and more you have spec breaks between the same family of materials. Let's say you have a spec break between a lean duplex and Saphorex. Now, if you don't check correctly, and then you have the lean duplex ending up in the place where you should have Saphorex, that's a huge problem that you want to avoid. So carrying out PMI during construction phase is also quite important. And, of course, you should include all appendages in your program. So not just the pipelines, but all attachments to pipelines should be considered. And the good thing about doing RBI is you don't need to check every single one, but you need to know which ones to check, which can be representative of the whole population that you have. And then I have the final case over here, which happened in a gas line, again running from the reactor to the scrubber. And this case is quite important because more and more we see these types of failures. I know of at least 3 or 4 of these types of failures happening in gas lines in the synthesis section, which are made from austenitic stainless steel materials. So during operation, they realized that they had some cracks in the pipeline, which was leading to leaks. So the plant had to be shut down, and then this section had to be removed and then replaced. When they cut them, and then we took a look inside, this is what we saw. So you see that actually the leaks originate in the heat-affected zone and at locations where you've had condensation corrosion. And beneath this condensation corrosion products, you have the cracks originating from inside the pipe through wall to the outside. This is not a phenomena that even we as Stami Carbon were familiar with. Because whenever there are cracks in, let's say, a gas phase, we expect that in the reactor at the top circumferential weld in the heat-affected zone and not in pipelines. So for us as well, this was quite new for us, and we had to really find out what is happening. We studied the problem quite in detail, and first of all, we realized that the cracks are intergranular. Because the material is austenitic, as soon as people see cracks, then they think, hey, it might be chloride related. But then if that was the case, then the cracks would be transgranular. But these were intergranular cracks. And for all the plants where we began to see this, it's also older plants, so plants older than 15 years old. And we were seeing them in only the austenitic stainless steel materials, particularly the 316L urea grade material. And also it was only occurring in the heat-affected zone of welds. The other thing that was important that we noticed is that at the crack tips, we always found corrosion products there. What this tells us is that this crack has been propagating for several years. So it's a process that takes a slow time to propagate. And that also indicates why we were finding it only in older plants. So actually now we had a few things. We have condensation corrosion, we have cracks which have corrosion product in them, which leads to leaks. We also looked at the grain size of the base material, which were quite larger. And then this pointed us to a new failure mode for gas lines in urea plants, which is strain-induced intergranular cracking. So this is something that we now have to incorporate among the failure modes when we are taking a look at the plants to help the plant operators with a lifetime assessment, for example. And another thing to point out is that this problem can happen on its own, but if you have contaminations of chlorides and sulfur also in your process side, it will actually make the propagation of the cracks much faster. So you should always make sure that you avoid contaminants from the process side. Yeah, I think I've already mentioned this. So now moving on to what Stami Carbon's idea is about carrying out the inspections of your pipelines using an RBI approach. I talked about criticality, where you have to rank your piping based on risk. And of course, the risk will change depending on what is passing through the lines. So we separate the lines into different categories depending on the process media. When looking at your criticality, you have to look at the threats from the process side and then the threats from the atmospheric point of view. You also need to have a total life cycle approach. Actually, this is the best. So if you are now in the construction phase, you can already start thinking about the RBI approach. So during the engineering phase, you need to select cost-effective materials, but then these materials should also be able to do the job. They should be placed in an environment where they can survive for at least 20 years. During procurement, you should have a robust quality assurance and quality control system in place to make sure that you are getting what you ordered. During the construction phase, inspections are quite important. At the equipment manufacturers, usually Stami Carbon is contracted then to visit and make sure that the vessels are being constructed according to specification, that weldings are being done correctly. Things such as painting and insulation systems are also quite important, because during painting, you should adhere to the specification on surface preparation and how to apply the coating, because improperly applied painting is actually worse than having no painting at all. And this is another important thing that we come across, that the insulation system should also meet specifications with respect to chloride content. I think recently the guideline is you should have less than 10 ppm of chloride in insulation material. And if you have older plants built in the 70s, then this requirement was not so stringent. And of course, during operations, you should carry out inspections, maintenance, and repairs, but these should be done in a proper manner. Because your RBI team can end up being quite large, because actually it is a multidisciplinary team, you should have clear segregation of responsibility so you don't have overlap, and that it is clear to members of the team what exactly their responsibilities are. And of course, as I mentioned earlier, you should involve your third-party contractors also in these teams. I've talked about how to look at the risk, but then what are the factors that you have to take into account? You need somebody on the team who actually understands the modes of failure. So if I take a pipeline, I look at the material of construction, I look at the process conditions, what can go wrong? I also need to look at where this pipeline is located. And looking at it from the process side and taking stainless steels, these are a few modes of failure. So you can have active carbamate corrosion in the liquid phase, and this happens when you have the potential of depletion of oxygen or stagnant conditions. You can also have condensation corrosion in the gas phase, depending on external and internal conditions. Pitting corrosion is also an issue, but honestly, this is not something that we see often. The trick for pitting corrosion is that if you do not see pits in your static equipment, then most likely they are not in the pipelines as well. We have strain-induced intergranular cracking, as I showed in case 4. And then you also need to consider things like fatigue. So if your pipeline is connected to vibration sources such as pumps or compressors, this also needs to be factored into your probability of failure. And this picture over here is a pipeline that is showing some condensation corrosion, and then this pipeline failed as a result of active corrosion. Yeah, but when we look at the atmospheric side as well, what can go wrong? And there, for stainless steels, and now I'm talking of austenitic stainless steel, so the BC materials, the main threats are from chloride stress corrosion cracking, either under insulation or under clamps. So maintaining proper insulation and jacketing is quite an important factor, because you might end up making sure that everything on the process side is perfect, but then you may end up having a failed pipeline as a result of neglecting what is happening from the outside. Now, coming to carbon steels, actually in the synthesis section, you don't really have carbon steel carrying corrosive media, but we still have carbon steel carrying liquid ammonia and also CO2. So from the process side, you should think about ammonia stress corrosion cracking and how to mitigate this. Do you check for the oxygen content in your liquid ammonia? Are you dosing with water to help prevent this? So from the process side, we look at ammonia stress corrosion cracking, but also for CO2 lines. Question to ask yourself is, do you have wet CO2, for example, coming to the bottom of the stripper? What is the water concentration? Because when you have water and CO2, and normally that line is not insulated or traced, if temperature drops below the dew point of the CO2, it will combine with the water to form carbonic acid. And that is also a threat from the inside, which you should think about, and then think about how am I going to identify this and how am I going to mitigate against this. But for carbon steels, as shown on this slide, most of the threats are actually from the outside. So you can have nitrate stress corrosion cracking, because urea plants, just based on where they are, close to ammonia plants and then other installations in the neighborhood, you have a lot of nitrates in the atmosphere. And then when you have rainfall or even water from your firefighting drills, or just dew falling at night, or breathing vents, these can all get actually nitrates into insulation if you don't have proper insulation and jacketing. You can also have crater type attacks on damaged coating, which is why when you want to repair this, proper surface preparation is important. We can talk about crevice corrosion at supports, and then crater type supports by intermittent use. So now that we've seen all of this, then you begin to think, well, how do I go about mitigating this by incorporating a sort of inspection methodology? But first, you are faced with a few challenges. You need to bear in mind that there's a large spread of piping. You have difficult accessibility. You don't have access to the insides, and then you also have insulation. So you should have a way to assess. And there, Stamicarbon can help you, because we take a look at all the information that you give to us. We also look at your history, maintenance upsets, and then help you to select at least, let's say, 20% of locations. And in there, you should have at least 80% of the things that can go wrong. You also need to have at the back of your mind, because when you are performing inspections, you could have various objectives. Are you going to check a damage that you already know of? Are you just making a survey? Are you removing insulation or keeping it in? Because that will affect the NDT methods that you are going to use. And we always impress upon plants that make sure that all personnel are aware that anytime they see something wrong, it might be as small as something on the jacketing, it should be reported so that it can be fixed. Yeah, something like this, if it is seen, it should be reported. So, because this here is just a space where moisture can enter and damage the surface of your pipeline. For the NDT methods that you can use, the traditional ones are the most reliable, but then that means that you need to take off insulation and jacketing at some locations if you're going to do UT, or if you're going to carry out dye penetrant testing. Even if you're going to, let's say, look into the pipeline, you need to disconnect some flanges and stuff like that to get access. So you can use the traditional methods, but that involves more work and planning. As time progresses, we get more and more sophisticated methods as well that can help you. So, you can use radiographic methods as well. This picture over here is an example. From this, you cannot tell, of course, the wall thickness of the pipeline, but at least you can see that you have some corrosion product gathering here, so then it alerts you that, hey, you have something happening from the outside, and you need to take care of it. And but it's not all about inspections. Also, when you are running the plants, there are several things that you can do to mitigate the risks that your pipelines are facing. Make sure for the austenitic stainless steel pipes that you are dosing with the correct amount of oxygen for passivation. The application of insulation and steam tracing is quite important for gas lines to prevent condensation corrosion. Select the proper materials of construction, and if you are not sure, PMI is your friend to cross-check. Avoid dead pockets and stagnant conditions. And then, of course, avoid all these dangerous guys like chlorides and sulfides. From the atmospheric side, so these are mitigation points from the process side, but you shouldn't forget about the atmospheric side as well. So make sure that you have a correct coating system for coated lines, and then you have the appropriate insulation materials with. I think you can hear me, right? Yeah, I'll just continue. Okay, so you need to make sure that you have the appropriate insulation material with as less chloride as possible. Correct installation of tracing to make sure that you have spacers in between your tracing lines and your process lines. And you have to have the proper jacketing, so you have a watertight insulation system. And anytime that you get a damage, please repair it as soon as possible. So, in conclusion, we need to, it's okay. Yeah. Piping systems deserve more attention than they've been getting, because actually most of the failures occur in the synthesis section of urea plants, at least in the piping much more than in the static equipment, because piping is neglected. To be able to do this in a more analytical and systematic way, you need to have a tool. And the tool that you can use is the RBI method. And when Stami carbon comes in for, let's say, an older plant which has been running for 15 years or more, we will help you with what is called a lifetime assessment. So we will take a section of the plant, take a look, especially the synthesis section, since that is the most vulnerable. We will take a look at the pipelines and then help you to determine what are the risks, and also for the piping, what is the remaining lifetime. But most importantly, we've given you a template for the risk-based inspections, because now you have the probabilities of failures, you have the risk rankings, you know what to check next time, because this is supposed to be a living document. When we give you the inspection interval, we will not come back and measure again, but then when you know the inspection interval, you should measure again. And then based on the corrosion rates that you get, now you can adjust your risks for the different types of piping, and you can also get a new inspection interval. But you can also plan for when when you need to replace a certain section of pipeline. So it's quite an important thing. Remember also that the RBI team should include all stakeholders, including external parties. The clear segregation of responsibilities is very important. There should be awareness of this so that when something goes wrong, people know to report it and report it correctly so that the appropriate actions can be taken. And remember that the threats are not only from the inside, but they are also external. And yeah, I think the reporting point is again repeated here. And please make sure that you don't end up in a situation like this where you have a forest growing, let's say, from your insulation material, because I don't think that you should feel very comfortable walking around a plant which is operating and then you have this condition. It's quite dangerous. Thank you very much for your attention. So if you have any questions, yeah.
What happened when you do you look at upstream. These control different time, as we said, to make the next scheduled time for making the inspection well. And also we have talks, for example, from now their experience to reduce the cost. Before we did make a lot of piping and we found it for nothing sometimes, especially for the normal area. You don't have to do them every 2 years or every 3 years. Now Yara has extended their inspection up to 4 years because they're looking for everything in a proper way, you see. Also, you make systematical way how to be inspected in a proper way, but there are some other factors which it's missing, you know, which cooperation between operation and maintenance for the feedback. For example, you make your schedule and you make it after 2 or 4 years to reduce the cost, because if you're finding in the previous history, you found this one, nothing, you'll concentrate on the critical area like synthesis area or some other things, corners, elbows, and some other things. But there are some other factors which are out of our control, which the feedback. What's the feedback? The most important thing, the process parameters. For some area, which if the process parameters, it changed, that means whatever you have done completely will be changed. Maintenance, they don't know that has happened. And sometimes they'll keep it confidential for a process because this is a process business, it's not related to maintenance. That's the mistake. I mean, the knowledge of the people to understand that cooperation between a process and maintenance, it should be done for your company to reduce the cost, to reduce the time, the downtime, to make a proper scheduling. That's very important, the feedback to make a proper scheduling.
Yeah. What you are saying is true and it's important. That is why we talk about the awareness and commitment of all stakeholders. Because again, it comes back to the point of people should understand, they should know what they are supposed to do, but also they should understand why they are doing it. So if they understand that by withholding this information, it has a negative effect on the RBI program, then these lines of communications will be made easier, because we are all working towards a common goal of making sure that the plant is running safely. And everybody should have a stake in this. So when something goes wrong, upset conditions, these should be reported, because like I mentioned, yeah, it will have an impact on your on the risk of whatever section that happened in.
Especially it's your company, because sometimes you'll bring steamy carbon. Steamy carbon,
they want to guarantee. They'll tell you you have to inspect it after 3 years, and they know 100% it can go up to 5 years. But internally, in some cases, you know that one because just not like that, because you know 100% because of your previous system, you have done it and you know it. That means the feedback is very important. Okay. Our guys here, they have a question about the elbows. Sometimes we found the elbow, and the elbow, sometimes it's not in our stock. Building up the elbows, is that okay? No problem. For us as a mechanical and as inspection, sometimes we give a recommendation to build it up for if it's not there, especially in the HP elbows. What's your opinion as a steel carbon about that? Overlay. Overlay.
Yeah, it depends. It will depend on the process conditions, where exactly this elbow is located. It will depend on the material of construction, for example. If it is a duplex pipeline and you want to build it up, we will tell you to be very careful because you can actually make the situation worse. Yeah, so you need a lot of expertise, which may not be available on the plant side. It also depends, for example, on the process conditions. Is this like a really high pressure line where failure has a lot of consequence? Then we can advise you. So in this case, it's not a yes or no answer. There are possibilities depending on the exact condition. Yeah, there are possibilities. So yeah. Thank you.
Good day. My name is Rafter Rawajda, planning engineer at Kimapco from Jordan. First of all, I would like to thank INFCO for best hospitality and wonderful workshop. It was an amazing time yesterday for me and my colleagues. Okay, today I will introduce a case study for how to minimize the actual between the planned and actual shutdown progress in potassium nitrate unit, which refer to NOB unit at Kimapco company. Here the outline. We have introduction for Kimapco history, Kimapco maintenance structure and activity, shutdown and maintenance philosophy, past example from past shutdown example, and historical data, maintenance difficulties, review for shutdown delay causes, action plan and result. First of all, here the Kimapco history. Kimapco was established at 1999 as joint venture between Arab Potash Company, the mother company here, and Camera in Finland. After that, at 2007, the Kimapco became fully owned by Arab Potash Company. The main product is potassium nitrate, NOB, KNO3. There is two material used to produce it. The ammonia from JPMC, Jordan Phosphate Mines Company, and KCl from ABC. The plant production capacity around 150,000 tons per year at 2003. After that, there is upgrade. The plant located at Industrial Zone Aqaba consists of 4 units, auxiliary boiler and nitric and utility, nitric unit, ion exchange unit, and NOB unit. In addition, the material handling for loading and packaging issues. Their expansion project was accomplished at April 2018 by installing a new MBU unit, NOB posting unit, to enlarge the capacity of production from 150,000 tons per year to 175,000 per year. Here the Kimapco maintenance structure. Kimapco, the maintenance department, has in-house technician team that all jobs, either daily or shutdown, are done by them, divided into 3 categories: mechanical team, technician team, and workshop team. Maintenance activity type: there is corrective type, preventive, and predictive. Corrective, to keep the equipment in operation time by repairing mechanical seal, bearing, oil makeup. Preventive, including the inspection round, which was daily issued using API Pro maintenance management software, and predictive through the DCS system data in order to monitor the health of equipment. Shutdown type and maintenance philosophy. We have 3 categories of shutdown. There is monthly shutdown, around from 12 hours to 30 hours, and there is every 3 to 4 month shutdown. It takes from 48 hours to 60 hours, and there is yearly from 7 to 10 days hour. Here the monthly, mainly for dryer washing, crystallizer washing, evaporator washing, for every 3-4 months, mainly for catalyst replacement, and yearly based on revamp for a certain equipment, such as reaction water condenser, overhaul turbine, expander, compressor, overhaul centrifuge, etc. All activity are shut down are placed at the beginning of the year at the budget based on operational requirement, taking into consideration with sales plan. Here the delay is calculated in hour. Our production rate is 18 ton per hour. The philosophy is to minimize deviation between planned and actual as much as possible. Our stream factor is 335 days for NOB unit. This case study is introduced for NOB unit, not MBU unit, but the approach later on will be applied to MBU unit. We have maintenance planning difficulties, problem defined, lack of traceability, manpower allocation, spare part availability, and learning by technician. Example from bus shutdown schedule. We have here example of task that cause delay in the bus shutdown. KK anti-surge tank flange not dripping by operator, so to be repaired and added to master shutdown list or the next shutdown list. The jobs was planned on shutdown schedule without a briefly defined requirement, manpower, spare part availability. The job took 16 hours instead of 3 hours. Some skills are not available because they are dedicated for another jobs, and shutdown extended around 1.5 hours out of 30 hours, which means production losses around 27 ton. Here historical data for 2016. The deviation between expected and actual is minus 41 hours, and there is a list of regular shutdowns. For 2017, same issues, but the deviation was minus 69 hours. Review for shutdown delay causes. We have a list for causes. Technicians are allocated as best unit based, not overall planned. Technicians are assigned by field engineer, not by planning. Worker hub from job to job. Workers stand around the job site. Responsibility for job that needs several skills as electrical, mechanical, welder. The job was assigned for more than one engineer, so the evasion of responsibility start appearing. Workers spend time standing around waiting for equipment to be surfaced. Unable to develop productive work rhythm to ensure time spent on the job. Here the action plan, we have defined 3 stages in order to improve the deviation and to minimize it. Screening, rearrangement, central planning. Start of screening. We define the problem, the nature of it, the priority. We categorize the jobs in 3 types. First, weekly task, shutdown task, and turnaround task. If the job I can do it in daily basis, I will do it in weekly plan. If I cannot and need to stop the unit, so I will shift it to next shutdown or the long-term shutdown. benefit suggestion shutdown list minimize as much as possible by doing some activity during unit running. Next stage is rearrangement. Here the layout for our plant. Nitric unit, auxiliary boiler unit, ion exchange unit, knob unit, potassium nitrate unit. Here the MB unit. Our case here to grouping all activities for the same unit for the same team. Determine the readiness date and time for servicing equipment for servicing in cooperation with the production team. Based on production shutdown sequence, focusing on certain unit till the other units will be ready for servicing. The benefit, transportation of technician and their tool will be minimized. Avoid waiting time resulting from non-readiness equipment. Central planning, we have action in order to enhance the manpower allocation and traceability for the workers. Each engineer prepared his work as per part for the framework time. Each worker prepared his tools before 1 day of shutdown. Assign one engineer for the job and assign technician name for it. Concept of unit-based technician was changed to plant-based technician. Central planning for manpower to be done by planning engineer. Build the standard time for achieving common job, such as replacing valve. It take 1.5 hours and need one mechanical and one electrical. Benefit, increase manpower utilization, minimize conflict in manpower allocation, minimize overtime, avoid work scope creep, provide rigid time frame, accountability will be more efficient. Here a template for the shutdown plan, and there's divided in the unit based, ion, knob, nitric, utility, whatever. Here the issue, status, name of the job, name of engineer, the mechanical technician name, and there's a traceability from to, etc. Here the achievement till end of November 2018. The improvement, the deviation will be 7.42 hours till now. إن شاء الله ما يصير شيء في شهر 12 صراحة. The production opportunity, we have losses in 2016 as deviation become minus 729 ton. In 2017, 1,235, and in 2018 till now, 130 ton positive production gaining from the new approach. And thank you. Any question? Okay.
What is the longest duration of shutdown you had? The longest duration. What is the longest duration?
For the regular or for the yearly?
Both.
For the regular maximum, if it's monthly, maximum 30 hours. If every 3 to 4, maximum 60 hours. If yearly, from 7 to 10 days. Except the expansion project at which was done at March, it take I think 21 days. But this is exception. It's not a regular shutdown. That's it.
So your presentation was on the regular one?
Yes, the improvement in the deviation of the regular shutdown, because already it's planned at the budget of the beginning of the year. Last year, yes.
Last year
we meet the KPI, our KPI, and this is reflect on our bonus at the end of the year.
Otherwise, before that, it was lower than that?
Yes.
Okay.
Already there is a target is defined by our GM, our GM, in order to meet it for each sector, such as maintenance or technical production, etc.
Do you have maintenance cost as an KPI also?
Yes, we have maintenance KPI already cascade down from operation manager to maintenance to our maintenance engineer.
So have you achieved any reduction in that?
This is one of the KPI reduction I achieved it.
Maintenance cost, money?
Yes, well, there is a reduction. but it's confidential here. Okay.
Thank you.
No problem. Okay. برش.
الحمد لله رب العالمين. فعاليات الورشة كورق عمل انتهت، ونأمل من الله سبحانه وتعالى يكون فيها الاستفادة الكافية من أوراق عمل البارحة، استغلال وتفعيل المعلومات الموجودة معنا من الأنظمة التي استثمرت سابقا، تحليل البيانات، وأيضا إفراغ العمليات التشغيلية وعمليات الصيانة من خلال المعلومات الموجودة، يعتبر متطلب رئيسي في هذا الأمر. ونسأل الله سبحانه وتعالى أن نكون سفراء لشركاتنا التي ابتعثتنا لحضور هذه الورشة، وبإذن الله سبحانه وتعالى يكون هذا العلم منقول من المحاضرين إلى الحاضرين إلى الناس الموجودين معنا زملاء في مواقع العمل، حتى نؤكد عملية نقل التكنولوجيا من خلال نقل المعلومات، من خلال التعامل في وضع هذه المعلومات موضع التنفيذ من خلال عملياتنا اللي نشتغل فيها. اليوم أيضا كانت محاضرات ممتازة جدا تقدم من ستام كاربون، البحوث الجديدة في التكنولوجيا، أدوارنا كمهندسين قائمين على التشغيل، و يعني تركيز البحث وتركيز أيضا النظر والتدقيق في معطيات التشغيل، وأيضا التعلم من تجارب الآخرين التي حدثت كحوادث أو كنقاط best practices معمول فيها من خلال مصممين التكنولوجيا أو موصى بها من خلال مصممين التكنولوجيا أو غيره. فبإذن الله سبحانه وتعالى يكون هذا العلم موضع التنفيذ حتى نستفيد منه وتستفيد منه الشركات والمستثمرين الذين يقفون خلف هذه الشركات. وإن شاء الله الآن يكون عندنا حفل أو عندنا فعالية توزيع الشهادات، شهادات الحضور على رؤساء وكل الشركات المشاركة. ونؤكد أيضا على أساس أن الغداء بيكون إن شاء الله في نفس المطعم، مطعم الطيبات اليوم بعد حفل توزيع الشهادات. وأيضا نؤكد إن شاء الله سيكون هناك عشاء رسمي ساحة المقابلة للمطعم في نفس الفندق، يبدأ من الساعة 7 بإذن الله سبحانه وتعالى. واستلمنا الآن قوائم الناس اللي لهم الرغبة في المشاركة في الجولة السياحية للاطلاع على معالم مدينة مسقط، وسيتحرك الباص بإذن الله سبحانه وتعالى الساعة 9 من أمام الفندق، والعودة بإذن الله سبحانه وتعالى نتمنى أن نعود على حدود الساعة 12، ولكن يعني نعمل حسابا على أساس أن تكون العودة على حدود الساعة 1 تحاشيا أو تلافيا لأي زحمة ممكن تحصل، لأن غدا آخر يوم من أيام الأسبوع، اللي عنده ارتباطات سفر أو غيره يعمل حساب في هذا الأمر. وإن شاء الله تكون إقامة مضي مسقط كانت طيبة، ويعني تطلعات وتوقعات من الورشة كانت بإذن الله سبحانه وتعالى مقابلة. ونعتذر كشركة أومشكور للأصالة عن نفسي وزملائي المشاركين وأيضا الإدارة الموجودة في مصنع الشركة عن أي تقصير حصل، سواء كان في التنظيم أو سواء كان في السكن أو سواء كان في تلبية المتطلبات اللي هي يفترض أنها تكون مطلوبة من خلالنا. ونتمنى أن نراكم في فعاليات أخرى في مسقط أو في عمان، بإذن الله سبحانه وتعالى نكون لكم مرحبين دائما. الآن ندعو الأستاذ عبد الله حتى يقدم كلمة الشكر أيضا للمشاركين، ومن ثم إلى توزيع الشهادة.
بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على رسول الله. اللهم اكتب الصالحات لأعمالنا وعلمنا ما ينفعنا وانفعنا بما علمتنا إنك أنت العليم الحكيم. ختام هذه الورشة نفسه وحضراتكم ونحب المعلومة الواحدة في الشركة قد تؤدي إلى وفرات كبيرة. معلومة واحدة ممكن أن تؤدي إلى عدم توقف أو تقليل فترة الشت داون أو حقيقة السبب شت داون والأنفورسين شت داون اللي تحصل أي وحدة منها. شكرا جزاك الله خير. أي معلومة تؤدي إلى تخفيض أي معلومة تؤدي إلى تسريع في الإنتاج، أي معلومة تؤدي إلى تطوير أو تغيير أو تحوير في مصانعنا ستؤدي إلى نتائج كبيرة اقتصاديا، وستؤدي إلى عوائد إلى شركاتنا أكبر بكثير مما نقوم باستثماره في كثير من الأحيان. حقيقة اتصل بي بعض الأخوة من الشركات وسيقومون بفعالية مشكورين عليها، وهو أنه سيأخذوا معلومة الموجودة هنا واللي حتكون على موقع الاتحاد ويعيدوا جزء من هذه المحاضرات ليقدموها كمحاضرة في شركاتهم، وإحنا على استعداد، بل على استعداد حتى لحضور المحاضرة أو أي معلومة تطلب من عندنا نستطيع أن نقدمها، سواء كانت المعلومة قادمة من الاتحاد أو نعود بنفسنا إلى تايسن أو إلى ستامي كاربون ونعزز هذه المحاضرة حتى تكون محاضرة فعالة في شركاتكم. وبهذا يكون حضور شخص أو اثنين أو ثلاثة هنا يستطيع أن يكون الفائدة تعم في الشركة. وهذا منهج حقيقة كنت أنا سابقا عندما كنت عضو في مجلس الإدارة ممثلا لجمهورية العراق، كنت أقوم في شركتي عندما كنت رئيس مجلس إدارة أنه عندما أوفد وفدا من لحضور الورشة أطلب أنه عند عودته أن يعد تقريرا ثم يعد برزنتيشن، يتعاون كل الفريق فيعد برزنتيشن. كان في العراق 4 شركات للأسمدة، وبعد أن يعدوا جيدا في شركتهم أوفدهم إلى الشركات الأخرى، وبذلك تكون الفائدة أعم. الفائدة عليه أولا لأنه أنت تعرف أنه أنت عندما تقرأ تفهم شيء، عندما تسمع تفهم شيء، لكن عندما تحاول أن تعيده وتشرحه سيرسخ في ذهنك، ويكون خاصة في أعمال التشغيل لما يكون الذهن مهيأ لأي صدمة يكون قابل لأن يستطيع أن يتخذ إجراء أو تفاعل أكثر مع المشكلة اللي تحصل في المعمل. لا أحب أن أطيل، فأنا أعتقد قد أخذتم ما يكفي من هذه المحاضرات، ولكن أود في هذه المناسبة وهذه العجالة أن أتقدم مرة أخرى لشركة أوموفكو على الجهود الكبيرة التي قدموها حقيقة، وقد شاهدتم حسن الاستقبال وحسن الضيافة وكرم الضيافة وبشاشة الوجه التي يمتاز فيها الشعب العماني. ليس هنا فقط في أوموفكو، انزل إلى الشارع ستجد الشعب البشوش المستقبل للمجتمع للضيوف بشكل يجلب الانتباه. تجد سواء دخلت إلى سوق أو دخلت إلى تجارة أو دخلت إلى شركة، تجد القلوب أوسع من الأرض وتجد العيون أوسع وتستقبل باستقبال أبهر لضيوفه. الشعب العماني شعب معروف بهذا، معروف بكرم الضيافة، معروف في سخائه ورجولته، وحقيقة هذه تسجل له وتسجل لأوموفكو هذه الأعمال. أيها الأحبة، لدينا المؤتمر الفني كما قلت إن عمان مضياف. المؤتمر الفني القادم للاتحاد العربي للأسمدة سيكون في عمان، وسيكون إن شاء الله تعالى ربما نحتاج يكون في نفس المكان هذا، وسيكون حافل في شهر أبريل من العام القادم إن كان في العمر بقية، وإن شاء الله نلتقي في ذلك اليوم
بارك الله فيكم. الآن نقدم شهادات لحضراتكم لتأييد حضور سعادتكم في هذه المناسبة. جزاكم الله خيرا وبارك الله فيكم، وأهلا ومرحبا مرة أخرى، وجزاكم الله خيرا، والسلام عليكم ورحمة الله وبركاته.